very good morning from Innsbruck, Austria, to Japan. I wish you a good afternoon. Before I want to start with this session, which I'm chairing, I want to congratulate the organizers for establishing such a great meeting in these very difficult times. And it's now my great pleasure to chair this session entitled Leading Edge of Science. And we have in this session 3 speakers. Before I introduce them, I want to show you this picture in the background of mine. It's a picture of Innsbruck, Austria. I have taken from my home just yesterday. There was fresh snow on the mountains, and we had beautiful weather. So you see the shape of the mountain looks a little bit like an infrared spectrum. And today we had, during the night, we had heavy snowfall. So we have again 30 centimeter of fresh snow. So today here we are all covered by water and water matrices. Okay, so now let us start with this session. And the first speaker will be Professor Mutsuo Iwamoto from Kagoshima Prefectural Food Technology Development Center in Japan, where he is Director General. And I only very briefly want to introduce him to you, as I think most of you already know him. Some important dates were 2001 until 2003. He was Director General and Secretariat of Research Council for Agriculture. Then he became Director General at the Japan International Research Center for Agricultural Sciences. And from 2005 until 2012, he was Board Chair at the Japanese Society of Techno-Innovation for Agriculture. And from 2015 until present, he's Director General at Kagoshima Prefectural Food Technology Development Center. His talk is entitled Encounter with Peculiarity in Physical Properties of Water and Expectation for Aquaphotomics. So this seems to be a very exciting and promising title. And I want to hand over now to Professor Iwamoto. Please give us your speech.
Thank you very much, Dr. Huck. I'm sorry that today that I'm going to speak in Japanese. So, first of all, okay, I speak the Japanese.
Okay, so from here I'm going to speak in Japanese. I have an agricultural background, and I have been an expert in food technology. So, of course, water has been something very important for me. And of course, since I was very young, I was interested in water. In 1978, I had an opportunity to work with Carl Norris. Yes, he is the father of near-infrared spectroscopy. I had an opportunity to work with him. During that time, Japan was importing a lot of rice from Canada and the United a lot of what I am researching is quite applicable to life. When water freezes, why does it start from the surface and not from the bottom? If you take a bath, like a really hot water boiling from the bottom of the tub. So even if you're boiling from the bottom, why is it that you can see the reaction on the surface, at the top level of the water? So all these things we know, but my experience with Professor Norris was an opportunity for me to think about why. This second derivative spectra, I happen to find evidence that each absorption must consist of 3 components of spectra. And I was able to find this out for the first time. Well, back in those days, we did not have computers. So a lot of the data processing was much harder, and now we can analyze all the data quite quickly. We suspected that something was going on, but in reality, it took us time to find out what was going on. So there is over 2,000 points where we collect the data, but not to our support from the computers. We're able to find out what those data actually meant. This is Carl Norris at Speltsville, at the Agricultural Research Center there. So he was about 30 minutes away from the research center. He passed away at the age of 96. So 3 years before he passed away, I was able to see him again, and he was such a gentleman. He gave me a lot of different kinds of thoughts on my research. He taught me a lot about life. He was very direct and honest. He lived for a very long time. He influenced me greatly. He influenced my life greatly. At the end, I did hear that physically he was getting weaker, but in the snow, he came to visit me. And to me, that was the last moment with him. So this is the Norris machine that I was talking about earlier. Carry 14. So this is connected. This instrument is computed to a 24-bit computer. And it was quite impressive that we were able to use this in the lab.
Well, at the time when I first looked at the spectral, I wondered what it was. And Norris said, I didn't know. And at Beltsville, there was a very large library operated by the Department of Agriculture, and I visited there to investigate what that is. And once every 5 years, a really famous professor wrote a textbook titled The Water. There are many equations in the textbook. I didn't totally understand what they are actually. And then after going back, I looked into a lot of books. And my basic textbook is titled Water and Solution, written by the professor of Keio University. And that book was published in 1977. That was around the time I studied about water and the spectrum. The book is edited more than 300 papers written in other overseas. And then he compiled over 300 papers into one book titled Water and Solution. Although it was not circulated now, but you can find that over internet, I believe. And agriculture and food science. And based on my knowledge or background, I study a lot about what they are. And the other book is titled The Mystery of 4 Degrees Centigrade, written by the professor of Keio University. This is also a basic point of water. And that book was highly useful for me as well. Anyway, the book titled Water and Solution impacted me a lot. And at the introduction, there is very useful sentences written there. I wonder why not so many Japanese professors wrote this kind of useful introduction. For the very beginner, it is very useful. The beginner should continue to read, even though you understand what is written there. It's very important to just keep reading. And then after gaining a broader understanding, broader knowledge of water, maybe you should go into detail by reading or by referring to other textbooks. Thanks to this book, I was able to learn a lot. And I actually visited him in person several times to talk about that. I was very happy in that sense. Peculiarity of water and the physical chemical properties of peculiar water. So this is summary from his textbook. There are 6 elements, 16 elements. At that time, it would belong to 6, like oxygen and selenium and tellur. Out of such hydrogen compounds, they have the biggest or highest melting point and boiling point. And furthermore, the fur and for the density of water is 4 degrees centigrade, precisely 3.98. This is a highest. Usually, when temperature increases, the density should be decreased. However, in case of water, at the point of 4 degrees centigrade, the density is the biggest. Then, as temperature goes down, the density also decreases. So, when we look at the bath, the surface water temperature is higher than the bottom part. Then the hot water goes down. And when the temperature is below 0 degrees centigrade, so usually the water becomes ice when the temperature is below 0 degrees. the temperature goes down from 10, 5, 4, 3, and at 4 level, the density is the biggest. That's why the hot water goes down and the lighter water goes up. In this way, the water becomes ice from the top part of water. And when water becomes solid, the density will be decreased. The density will be increased. So there are no other substances like water. And furthermore, surface tension. So other than the liquid metal like Hg, so water, the tension for surface tension of water is almost the biggest or largest. And there are some insects which can walk on water surface. And water strider can walk on water surface. However, it cannot walk on alcohol. Why is that? Both are liquid and mainly consists of OH. And furthermore, and the water has very big dielectric constant. And the water can dissolve substances so well. So once water is contaminated or polluted, it is very hard to clarify or purify it. That's why it is important for us not to contaminate or pollute water. In terms of water, we can say that water has some kind of peculiar characteristics. So this is about the chart mentioning the 4 degrees density. And this is boiling point and the melting point of water. So this chart came from old textbook. And the more the molecular weight is, the higher the boiling and melting points are. But oxygen or H2O, this has very high boiling point as well as melting point. Water, the boiling point of water should be -80 according to this graph, but actually the boiling point of water is 100, and the water is frozen at 0 degrees centigrade. So there are gaps between the actual temperature and the focused or projected temperature. And you can refer to the textbook in detail. This is about the shape of water molecule. So almost all the molecules are spiral shape. And very tiny with a diameter of 3.3 angstrom. And at room temperature, and the liquid water has very small molecules. And OH are covalent bonds. And the angle is 104.5 degrees. The angle is 104.5 degrees. This is not very, this is very complicated number. What this means is that O and H is connected with covalent bonds, and or the electronegativity of water is very high, and the electron is connected with covalent bonds, which stabilizes a molecule. So say that, so this is like a, this is not like a company who can share stocks 50%, 50%. Now, oxygen is negatively charged. This is what higher electronegativity means. On the other hand, hydrogen is positively charged. So these are one of the characteristics of water molecules.
So you can see here, the size of the molecules is, of course, an electronic thing. But as you can see, this is one part. The hydrogen is about a 10 yen coin, and the oxygen is about a 1 yen coin size. So it's very unstable and it keeps on moving. It's not really stable. That's why it reacts. And it's not very stable. So that is actually how water is, how water consists. So we take a look here. Here's the hydrogen and this oxygen, and one hydrogen, two hydrogens will be combined with the oxygen. The oxygen is inside the molecule and it's not going to go away. It's found in every molecule. So if you take this out and if you just take the outer layer, and there are 8 outer layers, and just the 2 outer layers is shared with the hydrogen. And it is possible for that to just instantly leave and separate. But as you can see, the water molecule is looks like this. The electron looks like this. And this format does affect how water actually activates. So this is the hydrogen bonds and cluster model of water molecule. And as you can see, it's charged in the minus part. So the hydrogen next to the minus part can bond easily. So this is the hydrogen. Okay, this is the water molecule. As you can see, how it connects to the other, how it bonds to the other. The hydrogen bonding is done like this. And this is how it bonds with the water molecule next to it, and how it bonds with the oxygen next to it. So just if you take a look at one hydrogen molecule, the hydrogen proton becomes a donor to the water molecule next to it. The hydrogen bonds in a cluster invites the other cluster to join. So you can see here, 1, 2, 3, 4. So water can be combined with 4 hydrogen points. So as you can see, That's why water can cluster like this. And this is the idea of the water molecule cluster. And if you take a look at the cluster, how it clusters with the hydrogen, this is the basics of the research of water. So to understand the structure of the water cluster and the hydrogen cluster is something, or this, and it is just one water. And then it happens once, twice, 3 times, as you can see. So the molecules are different molecules that come together. So of course, there are going to be big clusters and small clusters. So how do they get into big and small sizes? How is that created? So, you know, the ice in the Antarctic, if you can imagine that. And then, of course, there are big icebergs and there are just small icebergs floating. And we do see that. But to make it clear, why does happen? What are all the causes of that happening is something that we're trying to figure out. So there's the X-ray. How does the environment affect those changes? And how does that change the water? Yeah, how does that affect the water, and that affected water, how does that affect the environment and everything else? Yeah, so people look at me as I'm the water expert. A lot of it's a food science that is not really, it's just fake science, not something that you're the research. So it has been quite criticized by people. It has been criticized. However, but in reality, nowadays, people don't say that anymore. That was a long time ago. We've come a long way. So this is the cluster, how a cluster looks, a water cluster. So this is the model of the water structure. So there is the combined model. So this has been researched by Scheller, how it is combined and makes a cluster. So that was a hypothesis that's actually did exist. So new 1, new 2, new 3, how it changes, how it expands, how it becomes smaller. So the 3 different kinds of water clusters. Back in those days, we did not know a lot about the decomposition of the water. So that could be like liquid or gas. the microspectrum, the decomposition of properties were thought of that it is possible to decompose the water spectrum very easily into each component in use of the second derivative spectrum. So there is the naked one, and there are three different, there was a hypothesis that there were three different things going on. So the water structure, so clusters, it takes a couple of seconds or 10 raised to the power of -12 in that kind of circulation. I mean, if that was the range, it was still something understandable, but in a very short time, the water was able to combine.
So water is vibrating. So this is one of the hypotheses. So very fast vibration should be observed by eyes, like taken by camera. So speed of shutter is so rapid. So we need a highly sophisticated camera to catch such a fast motion. So these are quotes from the book. The word structure has three meanings regarding in response to the length of observation time. Even though the motion is instantaneous one, based on temporal axis, the one structure is formed. To this end, snap photo is needed with higher shutter speed to catch the very fast circulation cycle. So this is how the water structure is defined. This is schematic picture of structure of normal ice, or IH. So there are lots of ices, such as those under high pressure and so on. There are many types of ice, but this is about normal ice. And there are I structure, V structure, D structure, depending on the speed of taking a picture. I stands for instantaneous, V is vibration, and D is diffusion. So according to the speed of taking a picture, the object observed, as for I structure, the T is less than 10 to the 13th negative power. And as for V, T is from 10 to the 13th negative power to 10 to the 5th negative power. As for D structure, the structure will be taken, will be blurred. V structure is in between. Eisenberg and Kurzman defined in this way. At the same time, measuring technology or technique was invented according to the D structure, V structure, and I structure, and also the cycle or time. And based on this, biophysical events. I modified many information and compiled it into this chart. So surface tension measurement or viscosity or density, it takes time.
Professor Iwamoto.
So in this case, so time scale can be useful. And usually D structure, and in case of V structure, NMR, in the past, that was 10 to the 6 negative power. Maybe 10 to the 5th negative power and so on, but now the NMR is 10 to the 10th negative power.
Professor Iwamoto, here is your chair speaking, Christian Huck. May I kindly remind you that your
10
time
to the 10th
already
or 13th or 14th negative power, such a extremely rapid one cannot be observed by any technology except computer simulation. In the year 2000, nanotechnology should be one of the big themes of research in Japan. At that time, I was in charge of the administration of agriculture in the Ministry of Agriculture. And we were talking about what water molecules are. And research on water molecules should be included in the nanotechnology research. And thanks to that, and a lot of budget were allocated to Ministry of Agriculture. At that time, professor of Nagoya University or the director of laboratory in Kyoto did a large-scale project, which was even introduced in the Nature. When we look at the motion of water molecules, it was really interesting that as temperature goes down, the cluster appeared, and then ice grew around that.
Professor Iwamoto, please take care. You are running out of time. You are already some minutes over time. Yeah, you should have finished already a few minutes ago. So please see to come to an end.
Thank you. そういうことでですね、
So IR and Raman were effective 20 or 30 years ago. The temperature dependency was represented by second derivative spectrum. These are very old data. And this slide shows salt concentration, KCl and MgCl2. Important point here is that SL, S1, S2, the components. So although intensity is enlarged, but that's it. So in case of MgCl2, S0, so motion is so complicated. So magnesium, depending on salt concentration, disturbance is very different from each other. And when we try to control the temperature precisely from -10, from 140 degrees Celsius, we did research about ice as well by using different types of devices, homemade devices. Now, lastly, I'd like to talk about superheated steam. As you can see on this slide, This is liquid. For megapascal at 120 degrees Celsius, and almost all water molecules are gone at 1915 degrees. Wavelengths is divided, and when we compress it, the data are getting closer. And when temperature goes down, and from 1955 is integrated into one. So in case of steam, the wavelength is very low. Maybe this is partly because of rotation of water molecule. In other words, molecules will be more responsive. By changing pressure or temperature, we were able to get this kind of data. And this is very decisive result. Red rust. So when we pour hot water, we can reduce red rust. And the electron can be a donor of other electron. In this way, red rust can be reduced by pouring hot water. So high superheated steam is highly applicable to many occasions. We can only apply it to food processing, such as sterilization. And furthermore, dioxin, it can be applied to dioxin or other types of chemicals. In this way today, I have covered 3 conditions of water, roughly. And this is called nanocluster. Nanocluster is very important theme. This is my, nanocluster is now gaining popularity as a research subject among universities in Japan. And as a result, and a mechanism of function and measurement of water physical properties in which aquaphotomics can be applied. Anyway, aquaphotomics is born in Japan, but so there are few researchers who try to be in charge of interdisciplinary field. In particular today, people tend to hesitate to conduct interdisciplinary research.
Professor Iwamoto, here is your chair speaking. You are almost 10 minutes over time. Please,
I want to
see to finish your talk.
Okay, I will stop the few seconds after, please.
This is the last slide. I need more time to speak in detail. And if I have more time, I was able to tell you a very interesting story, but this is a time to end. Thank you very much for your attention.
I'm sorry, Dr.
Okay, thank you very much, Professor Iwamoto, for this very nice overview. I think due to the time which has really run out now, you are 10 minutes over time, we should maybe shift some questions to coffee break session, and we should continue with this session. There is one thing I want to point your attention at. It's on this Sunday in the afternoon at 4:45, there will be a speech from a colleague from my university, Christina Donauer. She will speak about extending the spectrum and spectroscopy of crystalline water ices, and she will give you some ideas about the research we are doing here in Innsbruck about the different forms of water. So this is directly related to this talk by Professor Iwamoto.
Thank you very much.
Okay, so thank you again for this very nice overview. I'm sure you have a lot of stuff to tell us, but now we have to continue. And now it's my huge pleasure to announce the next speaker.
Thank you. Thank you.
Next speaker is Professor Yukihiro Ozaki. I think most of you will know him. Yuki Ozaki received his PhD in 1978 from Osaka University, and he joined then Kwansei Gakuin University already in 89. Since 93, he was their professor at the School of Science and Technology until the end of March 2018. And now Professor Ozaki is emeritus professor of the university, and he has guest professor or scientist position at Keio University, Fukui University, Riken, and Toyota Physical and Chemical Research Institute. Now, Yuki is involved in studies of a wide range of molecular spectroscopy, covering from far UV to far infrared terahertz spectroscopy and also Raman spectroscopy. I can tell you, Yuki is a rather rare scientist who has been concerned with both electronic spectroscopy and vibrational spectroscopy. Yuki has been fellow of Royal Society of Chemistry, Japan Chemical Society, and Society of Applied Spectroscopy. He received several awards, including Bowman Michelson Award, Chemical Society of Japan Award, the Medal with Purple Ribbon, 2018, Pittsburgh Spectroscopy Award, and Charles Mann Award. I can tell you I had the huge pleasure to be a guest professor in 2014-2015 in Professor Ozaki's lab, and I really enjoyed so much the time and our very fruitful collaboration since that time. So today, Yuki will speak about molecular spectroscopy studies of water from far ultraviolet to far infrared terahertz and Raman spectroscopy. Okay, Yuki, I'm looking very much forward to your talk. Please, the floor is yours.
So thank you very much for your generous introduction. Thank you, Christian. So first of all, congratulations, Professor Chenkova, for your retirement. Also, congratulations on becoming a distinguished professor of Kobe University. Also, congratulations on establishing Aquaphotomics lab at Yunosato Spa. Congratulations. Okay. So today, my title today is Molecular Spectroscopy Studies of Water from Far-ultraviolet to Far-infrared Terahertz and Raman spectroscopy. Okay. So this is contents. First, I am going to have the introduction, then Raman spectroscopy on non-invasive analysis of water in an islands. The third topic is the far-ultraviolet FUV spectroscopy study of interfacial water on alumina. The fourth topic is IR and Raman spectroscopy studies of pure water and water in super-absorbent polymers. The last topic is concerned with NIR imaging study of water. So this is the absorption spectrum of water in the region from ultra vacuum UV to far IR. So this spectrum was prepared by Dr. Ikehata. Okay, he prepared this figure combining several absorption spectra. It's a very important and nice spectra. Okay? So by using this spectrum, you can learn many things about the water. Okay? So in the far IR region, you can see a band here. Okay? And in IR region, you can see OH bending vibration and OH stretching vibration. In NIR region, you can find the bands due to combination modes of water, okay? But please look at here, in FUV region, there is a huge, very steep bands due to XA band, electronic transition bands. So we just focused on this very exciting band, very intense. So we thought this band should be very useful for quantitative analysis of water and async aqueous solutions. Okay? So you can use FIR, IR, NIR, FUV, and also Raman spectroscopy for water research. So this is a very old study. I carried out this study almost 40 years ago. This is old but very important and very exciting study. Okay? I measured Raman spectra of whole islands by using this measuring system. Okay, here is islands. Okay, so these 4 regions of Raman spectra of rabbit lenses, nucleus center just here. Okay, for 1 month and 5 years old lens. So here you can see bands due to water, bands due to CH stretching mode of lens proteins. Okay, and here SH stretching mode of cysteine of lens proteins. And here you can see amide 1 band, amide 3, or phenylalanine bands. So all come from the protein, lens protein. Okay? So by measuring this spectrum, you can investigate the water and protein at the same time. Okay? This is really nice. I found this 40 years ago. Okay? This was really a great finding. Okay? And this is, please look at here, enlargement of this region and this region. So you can clearly see 2 bands, okay, due to water. Okay? So this one is due to the weakly hydrogen bonded water. This is strongly hydrogen water. But actually, at that time, I didn't know how many bands here. Okay? It was impossible to make a second derivative or some other spectral analysis. But please note, here is a weak bands due to amide band here. Okay? And with aging, intensity of these bands decreases, indicating that the content of water in islands decreases with aging. Okay? And please look at here. So SH stretching band of cysteine residue in lens protein decreases with aging, forming SS bond. Okay? So this is the tyrosine doublet region, tyrosine doublet here. Okay, in the case of aging, intensity ratio just change little. But on the other hand, in the case of cataract formation, the intensity ratio changes largely, significantly, showing that upon cataract formation, the amount of formation, some tyrosine residues of lens proteins became exposed to water. This is water region. So note that intensity of this one increases in the case of cataract formation. Okay? So upon cataract formation, the amount of water in a lens increased, and some tyrosine residues of lens proteins became exposed to water. So I found that Raman spectroscopy can be used to investigate the development of a disease. Okay? This is the second story. This is the second story. This is a far-ultraviolet FUV spectroscopy study of water. So here is the FUV region. FUV region is from 200 nanometer to 120 nanometer. Okay? So in comparison with other regions, for example, deep ultraviolet region, UV region, visible region, far ultraviolet region is rather wide in energy. Okay, wide energy. So this is the FUV spectra of water in this region. Okay, temperature-dependent change. So this is the first spectra of water, okay, observed by using spectrometer. Okay, so we succeeded in observing whole region of water spectra by using ATR technique. So this is our FUV spectroscopy team. Higashi, Ikehata, Morisawa, Goto, and Tanabe. This shows the motivation of our FUV studies of water. Okay? First, Higashi, who was mature PhD student from Kurabo Corporation. First, he was interested in this region, just normal UV region. So we measured UV spectra of these mineral waters. Okay? I asked him to go to supermarket to collect a lot of the mineral waters, and we measured UV spectra of these samples. So surprising enough, these mineral waters gives quite a different UV spectra. Okay? So in other words, UV spectroscopy can differentiate these kind of the mineral waters. We collected a lot of the mineral waters, all show different spectral patterns because they have the different ions, okay, different ions like this. Okay. Then we just, you see, all here going up, going up, going up, going up. So then we want to see this region, okay, this region, but not easy to measure this region because there was no commercial spectrometer above 190 nanometer. So there were three difficulties in the FUV region. For example, the absorbance is so intense. As I showed you, Oh, sorry. Sorry. As I showed you, you see, this band is so intense. Absorbance is so intense. Okay. And the second difficulty is the spectrometers must be vacuum evaporated or nitrogen gas purged. Also, there are very little applications. Okay. So we introduced ATR technique in FUV region. This was idea from Dr. Ikehata. Ikehata introduced the idea of ATR. Okay, so if you use a transmission spectroscopy, you have to use a rather thick cell. For example, the thick cell with the length of 0.1 millimeter or something like that. But if you use ATR prism, penetration depth here is only 100 nanometer. So you can get very thin cell here, okay? So water gives very nice spectra without saturation here, okay? So this was the first time we observed whole region of water bands. So this is the desktop ATR spectrometer system which we developed. So here is the sample component, and here is FUV monochrometer. Here is the ATR part, okay? Incident light is coming here, and this is, here is ATR prism, like this. This is the enlargement of ATR part. Here is ATR, incident light, and absorbed light here, okay? Sample is here. Okay, sample is here. And this is the sapphire internal reflection element, okay, And strong point of this spectrometer system is sample is in the air, but spectrometer here is nitrogen gas environment, okay? So inside and outside separated. So today, as one of the example of FUV spectroscopy studies of water, today I will talk about the FUV study of interfacial water on alumina. This study was carried out by Goto et al. By the way, tomorrow from 2 to 10, Professor Morisawa will talk about the investigation of the electronic state of water in hydrate melt using FUV spectroscopy. Okay? This is the purpose of the Goto's study. So XA transition, this band of interfacial water of nanometer thickness of alumina surfaces was studied by ATR FUV spectroscopy with variable incident angle method. So, incident angle is variable, okay, change, okay. So then this is the schematic diagram of water on the alumina. This is alumina, and this is the interfacial water structure. Here is the bulk water structure, okay. So here interfacial this bulk, and by changing this, you can change penetration depth here. Okay. So this is the FUV spectrum of liquid water with various incident angles. As the incident angle becomes from 58.4 degree to 71.8 degree, and this band show blue shift, also intensity increases. So this dependence on incident angle show that observed change of the XA bands ascribes to how much interfacial water contributes to the spectra. This is a calculated absorption coefficient spectra of bulk and interfacial phase. This spectra, this one, okay? Bulk spectra, bulk water, and this is interfacial water. These spectra were calculated from experimental spectra. Okay, so note that XA band of each phase is significantly different. The band maxima of interfacial water is higher, okay, higher. So red tailing here appears only in the interfacial water, okay, here. And we compare XA bands with the bands of ice, okay. Blue and green show the spectra of ice, okay. This is the bulk water. This is interfacial water, okay. So interfacial water, interfacial spectrum is closer to the ice spectra rather than the bulk spectrum, indicating that hydrogen bond state of interfacial water is very structured like the ice. And the red tail of the interfacial spectrum does not appear ice spectra, okay, only here, indicating that the red tail is peculiar to the interfacial water. Okay, let's move on to the third topic. And this is the IR and Raman spectroscopy studies of pure water and water in super absorbent polymers, this one. This study was carried out by Mr. Tatsuro Nas, myself, and Professor Sato. Okay, we already published this result. This is a structure of sap, and here is the CH change with some CO minus here, or yes, and here is the water, and like this. This is the normalized IR and Raman spectra of water. Okay, by calculating second derivative, you can find the three major peaks. This band here, near 3600 wave number, is assigned to dangling band. Dangling is just like this, okay? Dangling. This is dangling, okay? Dangling band, okay? So on this one, we assigned this band to weakly hydrogen bonding, and this band here are due to strongly hydrogen bonding. This band also has a nickname of collective band. Okay, so three major peaks. So this shows the Raman spectra of just water and water in SAP, super adsorbent polymer with the water content of 60%, 50%, 40%. This one is due to a CH stretching mode of SAP. Okay. So we carried out a curve fitting. You can see this one and this one and this one. So relative intensity of this and this change with change in the Raman spectra of SAP, just like this. Okay, relative intensity change. Okay. And this is the Raman spectra of just water, temperature dependence, and SAP or SAP, okay, with water content of 60%, 50%, and 40%, all temperature dependent results. Okay. And this one plots temperature dependent variation in the area fraction of SHB, strongly hydrogen bonding. So this one, okay, this one. This one. Okay. This one decreases. In the case of pure water, this one decreases with temperature. And yeah, SAP with 50%, 60%, or 50% also decrease. But in the case of SAP with 40% water content, changes are very little. Okay, and also, in the case of area fraction of weakly hydrogen bonding, changes in 40% water content rather small. Okay? So we interpret this result that there are stronger influence of the COO minus or CH2 groups because of low water content here. Okay? And water inside the 3D network can be more constrained by the interaction with the COO minus and CH2 groups, restricting the SHB species from breaking their bond states with increasing temperature. And we also plot the peak shift, okay, temperature-dependent peak shift. In the case of peak shift, again, SAP with water content of 40% show rather small change. Okay. Yes, small change here, but significant change here. Okay. Okay, this is the last topic. Okay. Last topic is NIR spectroscopy and imaging studies of water. The first topic is permeation of water into a tablet. This sort of investigation is very important for investigating tablet quality. Okay, tablet quality. And this study was carried out by Daitaro Ishikawa. Okay? So he measured NIR imaging with time, 0 minutes, 120, and 240 minutes. So So here is waterfront, okay? Waterfront going up, okay? So waterfront change very smoothly, indicating that quality of this tablet is very good, okay? So this sort of study can be carried out only by NIR spectroscopy. If we use IR, rather difficult to observe the changes in permeation for thick tablet. Okay? Only NIR allows this sort of monitoring. By the way, tomorrow from 2:10 to 2:30, Dr. Ishigaki will have a talk, assessment of, titled Assessment of Biological Functions of Metabolic Activity during embryogenesis by water analysis using NIR spectroscopy. Okay, so Dr. Ishigaki carried out a number of interesting NIR imaging studies. She used to investigate biomolecular distribution and molecular mechanism of embryonic in fertilized fish eggs. He used this high-speed NIR imaging system developed by Sumitomo Electric Corporation. So here is NIR camera named composition. There are two halogen light, and here is sample. This is high-speed system. You need only 2 or 3 seconds to get the imaging. Okay, and this one can be used for wide area monitoring, also micro NIR monitoring. So very nice instrument. Okay, so these are results obtained by this system. Obtained by this system only 3 seconds. It's a very beautiful result. Okay, this is the Medaka Medaka F. This is just a drawing picture. Okay, drawing picture. Here is the otilish structures of the inner ear. This is maybe an eye, I think. So this is just picture. This is optical imaging. Okay, optical imaging. These are NIR imaging. Okay. So these NIR imaging were obtained by using the intensity of the band at 6191 wave number due to CH2 and CH3 combination band. So you can see, for example, fatty acid, distribution of fatty acid. Okay? And this band is due to the NH deformation combination from protein. So this shows the imaging of distribution of protein. Okay, so protein distribution and fatty acid distribution. Protein is rich in membrane, also here, and also eye. Okay. So this is the results of the normal egg. This is the low temperature cultivation. This is just the this egg was made by frozen. Okay, so this is the an irregular egg. Okay, so this is the lipid results, protein results, and unsaturated fatty acids. So in comparison with a normal egg, abnormal egg show different imaging pattern. Okay, the last one is concerned with non-strain. Today I just forgot to bring the results of water, but you can also make the imaging of water, strongly hydrogen bonding water or weakly hydrogen water distribution. Sorry, I just forgot to bring. So this is a last example. This is a non-staining blood flow imaging using optical interface due to Doppler shift and NIR imaging of molecular distribution in developing fish egg embryos. So this is a system. This system was originally proposed by Professor Ishimaru of Kagawa University and Aoi Electronics at Takamatsu fabricated this system. Okay, this is a light source and lens, and this is the hyper imaging unit, and this here is InGas camera. Okay. This is hyper imaging unit. Here is a sample here. Okay. So this is the result: non-staining blood flow image. So you can using by this band or this band, you can see blood flow. Okay, blood flow imaging just like this, or heart. Okay, imaging. So this is a nice demonstration of potential of NIR imaging in investigating many components in egg. This is the conclusion. So what are research conclusion for one is water is really challenging, very attractive and interesting, but not so easy, maybe forever. Okay. The second conclusion is we have several kinds of eyes, various kinds of techniques, and various kinds of spectral analysis method. Collaboration is very important among researchers who use the different techniques. And also important thing is comparison of experimental studies and theoretical studies. Okay. And one can use FUV, NIR, Terahertz, FIR, and Raman. Each method has significant advantages, but at the same time also limitations. We have to know both. Okay? And the last but not at least, we have developed various kinds of application studies. And application studies, application to bioscience, polymers, pharmaceutical science, tablets, foods, stones, natural water, and so on. So application studies often produce very interesting basic science. Okay, so this is very important one. So thank you very much. Thank you.
Thank you very much, Yuki, for this very nice and excellent overview. Especially FUV spectroscopy is really something quite new. First, I want to check if there is one maybe question from the audience. Maybe we have time for one quick question. I see nobody type something in the chat. Is there someone who wants to ask a question? This seems not to be the case. So, Yuki, maybe I may ask you very briefly one question. How do you judge the sensitivity of FUV compared, for example, to NIR spectroscopy to external perturbances like, for example, temperature changes? We know NIR spectroscopy is very sensitive to temperature changes, and we can monitor this also in water bands. If you compare FUV with that, is it more sensitive to temperature changes, or is it less?
Oh, it's very difficult to compare. I've never tried, but yeah, I know both. But FUV is also very sensitive with temperature. This is temperature dependent of water band. Okay, so usually very sensitive. Yes, very sensitive, okay. And also, you see, FUV band is very intense. Okay, so this one you can investigate change using this steep band against perturbation. Okay. Okay. Mm-hmm. Mm-hmm.
Yeah, thank you very much, Yuki. Okay, so I think we have to continue due to the time limitations. Thank you once again, Yuki. It was a huge pleasure to hear your excellent talk.
Excuse me, Christian?
Yes? Yes?
Rumiana has a question.
Okay.
No, I have just a comment. The results about the interfacial water are very similar with what we obtained with infrared. And I think we have to combine these two. And the results about the interfacial water with UV are very interesting. And they're very similar to what we have obtained with infrared. So I think if we do two spectroscopy, hyphenated, UV and infrared, we might really understand what is happening on the interfacial stage.
Okay. So thank you very much for your comment. Please send me a paper or a report or something like that. Okay.
Okay. Thank you very much indeed. Appreciate it. Thank you.
Okay.
Okay. Thank you very much.
Thank you very much
for your comment. And yeah, so let us continue with the next presentation, which will be delivered by Professor Masato Yasui. Professor Yasui, he is also chair at the Department of Pharmacology at the Keio University School of Medicine, Tokyo, Japan. And he has a very exciting and interesting curriculum vitae. So he spent several years, for example, in Sweden, in Karolinska Institute, which is also quite famous. Then 1997 until 2000, he was postdoctoral research fellow at the Johns Hopkins University School of Medicine in USA. And it was in 2006 when he returned as a professor and chair to Keio University. Since 2015, he is vice dean. And since 2018, he's a director at the Keio Global Research Institute in Tokyo. His talk is entitled Water Biology and Medicine, Roles of Aquaporins in Biological Systems. I'm looking very much forward to hear your talk. Please.
Thank you very much for a nice introduction. And I'd like to sincerely congratulate Professor Tsenkova for your achievement and happy retirement and your future research. Please just enjoy your research and life. So since I'm a researcher in basic medical science and also the physician, pediatrician, I'd like to talk about water from the aspect of biology and medicine. So this picture shows the human fetus, just 10 weeks old. At this age, 95% of our body is water. You can easily imagine by looking at this picture. This was taken by a very famous Swedish photographer, Nielsen. And this ratio, the water content, is decreased gradually. This is at the time of birth. And at the time of birth, significant shift in the water distribution in our body occurs. That's one of the reasons why I got interested in water biology when I was pediatric resident. And we can say our planet, Earth, is a water planet. And this is very beautiful, and 70% of surface of Earth is water, sea water. And here at the bottom, sorry, in Japanese, 川のせせらぎ、飲む水、浴びる水、流れる水のありがたさを実感する。This is the words by astronaut Mr. Noguchi. As you know, he spent 6 months in the space shuttle, out of Earth. And when he returned to the Earth, this was the first comments. So he really realized the importance of water, not just water, but massive amount of water and water flow. I think this is very important. And when we think about the role of water in our body, physiology, exchanging the water, this is very important. So every day we drink the water, several liters, including the food water, and get rid of water by urine or stool and sweat. And also, circulating the water in our body is also very important by blood flow or lymphatic drainage or cerebral spinal fluid as well. So these two very fundamental feature of the water in the body makes us healthy and happy. And if you look at here, in the peripheral tissues, blood flow is always exchanging many molecules, including waters, between the cells and bloodstream. This is at the capillary stage. And if we further zoom in, here's the capillary and interstitial fluid, and this is the cells. And water is also exchanging between cells and bloodstream via interstitial fluids. And aquaporin water channel is mainly expressed at the cell membrane, right here. And this is the schematic model of cell membrane, which is the lipid bilayers. Water can be permeated through the cell membrane by simple diffusion on the left panel shows. On the other hand, water also can be transported through such as water channel proteins. If we have this kind of protein, we can expect massive water movement and also, more importantly, water permeation through the cell membrane is regulated. That's why when we play a tennis outside, we get sweat and our urine should be concentrated. On the other hand, if we go to the pub and drink a lot of beers, everybody wants to go to the toilet soon. So the urine is diluted in that case. This kind of regulation is very important to maintain our water homeostasis in the body. And because of discovery of this water channel aquaporin, my boss Peter Agre at the Johns Hopkins University won the Nobel Prize in 2003. Actually, I was sitting around here. That was just fantastic. I hope Professor Tenkova will take me there once again in the near future. And this is the actually movie based on the molecular dynamics simulation, the computer calculations. I hope this works. Oh, yeah. And one of the water molecules is colored with yellow. So if you just look this yellow water molecule, you can easily understand how the water is permeated by this water channel protein. And this is the calculation only within 10 nanoseconds. So I showed this movie at the very, very slow motions. And actually, the movement of water is very fast. 3 times 10 to 9 water molecules can be permeated through this aquaporin water channel per second. And in your body, one single blood red cells has 300,000 copies of this aquaporin. So you can imagine how fast we always exchanging the water between the cells and others. And this is the actually snapshot. Water is now just about passing through the narrowest part of the aquaporin water channels. And Dr. Iwamoto explained the water can make up to 4 hydrogen bondings. At this moment, this water molecule is always making the 4 hydrogen bonding with the amino acid residue of aquaporin. That means this water molecule cannot be making the hydrogen bonding with other water molecules. That means this water molecule is always isolated from other surrounding water molecules. So this is, aquaporin is always producing the vapors of the water molecules. I think this might be very important. We still don't know the functional meanings of this mechanism. But that's one of the reasons why I got interested in the aquaphotomics and started collaboration with Professor Tenkova. And this is the preliminary data. Actually, we initiated this collaboration about 10 years ago. And please look at the left panel. Here, this is the spectral pattern of the CHO cells without aquaporins. And the bottom shows the CHO cells expressing aquaporin. The big difference between these two, this sharp band around the 1400. This might indicate the producing the free water, S0 free water. So if this is the case, our hypothesis is correct. And in the human, we have 13 kinds of aquaporins, and each of them has a unique distribution. For example, aquaporin 0, which is only expressed in our eye. Dysfunction of this aquaporin developed the cataract. And aquaporin 2 is only expressed in the kidney, which is very important to concentrate of our urine. And today, I'm going to talk about aquaporin 4, which is abundant in our brain. And in the brain, mammalian brain, we have aquaporin 4. And in the brain, we have mainly 2 kinds of cells. One is the neuron, the other is glia cells. One of the glial cells is the astrocyte. Aquaporin 4 is not expressed in the neuron, but exclusively expressed in the glial cell astrocytes, and not diffusely expressed the astrocyte cell membrane, but only limited to the process which is facing blood capillary and brain surface, pia and surrounding the ventricles. These unique distribution of aquaporin 4 strongly suggest aquaporin played a very important role to exchange the water between brain parenchyma and blood or CSF. And many researchers already found aquaporin 4 involved in the development of brain edema. So clinically, this is very important. And recently, we also identified this is caused the autoimmune diseases, NMO, neuromyelitis optica. So we developed the antibodies against this aquaporin 4, which develop these diseases. But we still don't know the physiological relevance of these aquaporins. I already talked about the importance of lymphatic drainages. But if you look at here, you may notice this is a very big difference of the lymphatic system from the circulation system. If you look at the brain, there is no lymphatic capillaries. Brain is only exception. So we really don't need lymphatic system in the brain. I don't think so, and probably most of you agree. The role of lymphatic system a lot, but one of them is the clearance of the waste. And in 2013, the Professor Nedergaard group demonstrated very interesting idea. Although there is no lymphatic capillaries in the brain, there is the convective flow in the brain parenchyma from artery side to the vein side. And aquaporin 4 play critical role to create and maintain these flows. And this flow play very important role, get rid of waste of the brain from the brain, such as amyloid beta. And more interestingly, they also shows this flow is activated during the sleep. Why we need sleep? If this hypothesis is correct, we need sleep for the brain clearance. And actually, they also injected radioactive amyloid beta into the brain parenchyma and compared the clearance between wild-type mice and aquaporin 4 knockout mice. And as you see here, in aquaporin 4 knockout mice, this amyloid beta clearance is significantly delayed, suggesting aquaporin 4 play critical role to get rid of amyloid beta from the brain. And we also inject some dye into the CSF through the cisterna magna and observe the distribution of this dye and by comparison between wild type and knockout. As you see here in knockout, distribution is very, very limited. So this taken together, aquaporin 4 very important role for the brain water dynamics among CSF, brain parenchyma, and blood flow. So taken together, we hypothesize aquaporin may play a role or involved in the pathogenesis of Alzheimer's diseases. In Alzheimer's diseases, amyloid beta accumulation always occurs. And some of the Alzheimer's patient is familiar Alzheimer's disease. In that person has the mutation in the genes which is involved in the production of amyloid beta. So many researchers try to transfer that mutations into the mice called transgenic mice. These transgenic mice produce amyloid beta a lot. But unfortunately, these mice did not reveal the typical phenotype of Alzheimer's diseases. So what we did, we combined this Alzheimer's disease mouse model and aquaporin for knockout and see what happened. And this graph shows the recording of the mouse movement, and axis shows the time in one day from 6 a.m. to 6 p.m. So on the left half shows during the daytime. And as you may know, mouse is sleeping during the day and start to move during the night. And there are 3 types of mice here. And green indicates the Alzheimer's disease mouse model mouse. And blue indicates aquaporin for knockout mouse. And red is combined. And here's 20 weeks old mice. At this age, there is some difference. And 4 weeks later, 24 weeks, we can see a progressive difference between this double transgenic and the others. And even after 4 weeks later, 28 weeks old, this difference is obvious. At this stage, we can realize the difference. But 24 weeks or 20 weeks, by our eyes, we don't see the difference. And 30 weeks later, 30 weeks old, we can see more significant difference. And the next slide shows at the age of 36. And there are 4 kinds of mice indicated here. And you already noticed one of these 4 is very different. This is one. This mouse never moves. And at this age, this mice, double transgenic, always has shows the seizures. Seizure is one of the unique characters of the later stage of Alzheimer's diseases. And mouse lifespan is about 2 years, but this double transgenic mice always died right after 1 year old. I will skip this. And what happened? We tried to examine the mechanism. And if you look at the 20 weeks of age between, this is the Alzheimer's transgenic mice and with aquaporin knockout, this blue indicates the amyloid plaque. So you can see the difference in the size of amyloid plaque at the age of 20. But more obviously, at the age of 36, you can see the green line. What this indicates? This indicates amyloid beta is accumulated through the vascular structure. So we observed the perivascular accumulation of amyloid beta observed in transgenic mouse model with aquaporin for knockout background. And this is another mouse model of Alzheimer's diseases. As you may hear about the tau proteins, abnormal phosphorylation of tau protein also develop Alzheimer's diseases. And at the age of 9 months old, you can see atrophy of hippocampus and temporal lobe. And with aquaporin knockout, you can see such a huge atrophy. There is almost nothing in temporal lobe, and hippocampus atrophy is also more obvious. So actually, neuronal death occurs. This is a collaboration with the Professor Mutsuo at the University of Tokyo. And not only Alzheimer's diseases, even ALS, amyotrophic lateral sclerosis, we have the ALS mouse model. If we combine ALS mouse model and aquaporin 4 knockout, disease onset is going to be much earlier. So aquaporin 4 also, to some extent, involved in the development of ALS. And I don't have time to talk about much about our current project, but we try to visualize the water in our body, both at the macroscopic level and microscopic level. And microscopic level, we applied a nonlinear two-photon microscope. And we try to visualize water vibration by coherent anti-Stokes Raman scattering. Recently, we switched to stimulated Raman scattering by collaborating with Professor Ozaki at the University of Tokyo. And at the macroscopic level, we also level the water with the stable isotope, O17 water, and apply this for the MRI imaging by collaborating with Professor Kudo at the Hokkaido University. And also, we try to visualize in vivo imaging of these paravascular spaces, which most of the researchers recently believes we have the lymphatic flow, these paravascular spaces. That's why this is very important. So we succeeded in vivo imaging of these spaces. If we compare the control wild type and aquaporin 4 knockout after water intoxication, so after brain edema, in the control after brain edema, this space is narrower, almost nothing occluded. However, aquaporin 4 knockout, nothing happened. So we now try to quantify this space. And try to understand the role of this regulation of paravascular spaces in the certain physiological conditions. So this is the one which I talked about, the macroscopic brain water dynamics imaging using the stable isotope. We try to inject this stable isotope water, or 17 waters, into venous or directly into the CSF, and make the MRI images. And I don't show the data here, but we also observe the significant difference between aquaporin 4 knockout and wild-type mouse, suggesting aquaporin 4 again play a very important role in the brain water dynamics. Okay, thank you very much for your attention.
Thank you very much, Professor Yasui, for this very nice and impressive talk and overview. Are there some questions from the audience?
Professor Huck, can I ask one question?
Yes, please.
My name is Masato Takeuchi from Osaka Prefectural University. Thank you, Professor Yasui. You mentioned about the role of aquaporin for A-beta transfer. How about the A-beta 142?
Actually, yeah, as you pointed out, we have A-beta 22 and 20. 20 is more soluble. And I didn't show the data, but we performed the microdialysis experiments and quantified A-beta 40 and 42. And actually, A-beta 42 in the plaque, there is no significant difference between the wild type and aquaporin 4 knockout. However, A-beta 40, more soluble type, at the age, we observe the difference between wild type and knockout.
Okay, thank you very much.
Okay, thank you. Are there some other questions? If this is not the case, I want to thank you again for this very nice talk. And then I will close this morning session, Leading Edge of Science. I thank you all very much for your very kind attention. We will now move into a coffee break for, I think, lasting 20 minutes, and will then continue at 5:20 with the next session entitled Further Development. So please enjoy your free coffee break and return in time. Thank you very much.